In mathematical optimization, the push relabel algorithm is an algorithm for computing maximum flows. The name push relabel comes from the two basic operations used in the algorithm. Throughout its execution, the algorithm maintains a preflow, and gradually converts it into a maximum flow by moving flow locally between neighboring vertices using push operations under the guidance of an admissible network maintained by relabel operations. In comparison, the Ford-Fulkerson algorithm performs global augmentations that send flow following paths from the source all the way to the sink. The push relabel algorithm is considered one of the most efficient maximum flow algorithms. The generic algorithm has a strongly polynomial low-time complexity, which is asymptotically more efficient than the O-Edmonds-Karp algorithm. Specific variants of the algorithms achieve even lower time complexities. The variant based on the highest label vertex selection rule has O-time complexity and is generally regarded as the benchmark for maximum flow algorithms. Subcubic O-time complexity can be achieved using dynamic trees, although in practice it is less efficient. The push relabel algorithm has been extended to compute minimum cost flows. The idea of distance labels has led to a more efficient augmenting path algorithm, which in turn can be incorporated back into the push relabel algorithm to create a variant with even higher empirical performance. History. The concept of a preflow was originally designed by Alexander V. Kazanov and was published in 1974 in Soviet mathematical doklady 15. This preflow algorithm also used a push operation, however, it used distances in the auxiliary network to determine where to push the flow instead of a labeling system. The push relabel algorithm was designed by Andrew V. Goldberg and Robert Tarjan. The algorithm was initially present in November 1986 in STOC 86. Proceedings of the 18th Annual ACM Symposium on Theory of Computing, and then officially in October 1988 as an article in the Journal of the ACM. Both papers detail a generic form of the algorithm terminating in O along with AO sequential implementation, AO implementation using dynamic trees, and parallel distributed implementation. Concepts, definitions and notations. Consider a flow network with a pair of distinct vertices and designated as the source and the sink, respectively. The relation denotes the capacity of each edge. If, then we assume that a flow on is a real function satisfying the following conditions. The push relabel algorithm introduces the concept of preflows. A preflow is a function with a definition almost identical to that of a flow except that it relaxes the flow conservation condition. Instead of requiring strict flow balance at vertices other than S and T, it allows them to carry positive excesses. This means that in a preflow the total flow into a vertex can exceed the flow out of the vertex. Put symbolically, a vertex is called active if for each, denote its residual capacity by. The residual network of with respect to a preflow is defined as where the residual edges are defined as. If there is no path from any active vertex to T in, then preflow is called maximum. In a maximum preflow is equal to the value of a maximum flow, if is the set of vertices from which T is reachable in, and then is a minimum ST cut. The push relabel algorithm uses a non-negative integer valid labeling function which makes use of distance labels, or heights, on vertices to determine which vertex pair should be selected for the push operation. This labeling function is denoted by. This function must satisfy the following conditions in order to be considered valid. In the algorithm, the height values of S and T are fixed. Is a lower bound of the unweighted distance from U to T, and if T is reachable from U. If U has been disconnected from T, then is a lower bound of the unweighted distance from U to S. As a result, if a valid height function exists, there are no ST paths in because no such paths can be longer than. An edge is called admissible if the network when is called the admissible network. The admissible network is acyclic. Operations initialization. The algorithm starts by creating a residual graph, initializing the preflow values to 0 and performing a set of saturating push operations on residual edges exiting the source, where VVS. Similarly, the label heights are initialized such that the height at the source is in the number of vertices in the graph h equals v, and all other vertices are given the height of 0. Once the initialization is complete, the algorithm repeatedly performs either the push or relabel operations against active vertices until no applicable operation can be performed. Push. The push operation applies on an admissible ousedge of an active vertex U in GF. It moves units of flow from U to V. Push. Assert E U greater than 0 and H U equals H V plus 1 delta equals min F U V plus equals delta F V U equals delta E U equals delta E V plus equals delta A. Push operation that causes F to reach C is called the saturating push, since it uses up all the available capacity of the residual edge. Otherwise, all of the excess at the vertex is pushed across the residual edge. This is called an unsaturating or non-saturating push. Relabel. The relabel operation applies on an active vertex U without any admissible out edges in GF. It modifies H to the minimum value such that an admissible out edge is created. Note that this always increases H and never creates a steep edge, which is an edge such that CF greater than 0, and H greater than H plus 1. Relabel. Assert E U greater than 0 and H U less than equals H V V such that F U V less than C U V H U equals min plus 1. Effects of push and relabel. After a push or relabel operation, H remains a valid height function with respect to F. For a push operation on an admissible edge, it may add an edge to F, where H equals H minus 1 H plus 1. It may also remove the edge from F, where it effectively removes the constraint H plus 1. To see that a relabel operation on vertex U preserves the validity of H, notice that this is trivially guaranteed by definition for the out edges of U in GF. For the in edges of U in the GF, the increased H can only satisfy the constraints less tightly, not violate them. The generic push relabel algorithm. Description. The following algorithm is a generic version of the push relabel algorithm. It is used as a proof of concept and does not contain implementation details on how to select an active vertex for the push and relabel operations. This generic version of the algorithm will terminate in O. Since H equals V, H equals 0, and there are no paths longer than V minus 1 in GF, in order for H to satisfy the valid labeling condition, S must be disconnected from T. At initialization, the algorithm fulfills this requirement by creating a preflow F that saturates all out edges of S, after which H equals 0 is trivially valid for all VVS. T. After initialization, the algorithm repeatedly executes an applicable push or relabel operation until no such operations apply, at which point the preflow has been converted into a maximum flow. Generic push relabel ST. Create a preflow F that saturates all out edges of S. Let H S equals V. Let H V equals 0 VV S. While there is an applicable push or relabel operation, execute the operation correctness. The algorithm maintains the condition that H is a valid labeling during its execution. This can be proven true by examining the effects of the push and relabel operations on the label function H. The relabel operation increases the label value by the associated minimum plus 1, which will always satisfy the H plus 1 constraint. The push operation can send flow from U to V if H equals H plus 1. This may add to GF and may delete from GF. The addition of to GF will not affect the valid labeling since H equals H1. The deletion of from GF removes corresponding constraints since the valid labeling property HH+1 only applies to residual edges in GF. If a preflow F and a valid labeling H for F exists, then there is no augmenting path from S to T in the residual graph GF. This can be proven by contradiction, based on inequalities which arise in the labeling function when supposing that an augmenting path does exist. If the algorithm terminates, then all vertices in V, S, T are not active. This means all V, V, S, T have no excess flow, and with no excess the preflow F obeys the flow conservation constraint and can be considered a normal flow. This flow is the maximum flow according to the max flow min-cut theorem, since there is no augmenting path from S to T. Therefore, the algorithm will return the maximum flow upon termination. Time complexity. In order to bind the time complexity of the algorithm, we must analyze the number of push and relabel operations which occur within the main loop. The numbers of relabel, saturating push and non-saturating push operations are analyzed separately. In the algorithm, the relabel operation can be performed at most less than 2 times. This is because the labeling H value for any vertex you can never decrease, and the maximum label value is at most 2 for all vertices. This means the relabel operation could potentially be performed 2 times for all vertices V, S, T. This results in a bound of O for the relabel operation. Each saturating push on an admissible edge removes the edge from GF. For the edge to be reinserted into GF for another saturating push, V must be first relabeled, followed by a push on edge, then U must be relabeled. In the process, H increases by at least 2. Therefore, there are O saturating pushes on, and the total number of saturating pushes is at most 2 VE. This results in a time bound of O for the saturating push operations. Bounding the number of non-saturating pushes can be achieved via a potential argument. We use the potential function phi equals UVE greater than 0, H. It is obvious that phi is V initially and stays non-negative throughout the execution of the algorithm. Both relabels and saturating pushes can increase phi. However, the value of phi must be equal 0 at termination, since there cannot be any remaining active vertices at the end of the algorithm's execution. This means that over the execution of the algorithm, the non-saturating pushes must make up the difference of the relabel and saturating push operations in order for phi to terminate with a value of 0. The relabel operation can increase phi by at most. A saturating push-on activates V if it was inactive before the push, increasing phi by at most 2 V1. Hence, the total contribution of all saturating pushes operations to phi is at most. A non-saturating push-on always deactivates U, but it can also activate V as in a saturating push. As a result, it decreases phi by at least H minus H equals 1. Since relabels and saturating pushes increase phi, the total number of non-saturating pushes must make up the difference of plus 4 V2E. This results in a time bound of O for the non-saturating push operations. In sum, the algorithm executes O relabels, O saturating pushes and O non-saturating pushes. Data structures can be designed to pick and execute an applicable operation in O time. Therefore, the time complexity of the algorithm is O. Example: the following is a sample execution of the generic push relabel algorithm, as defined above, on the following simple network flow graph diagram. In the example, the H and E values denote the height and excess, respectively, of the vertex during the execution of the algorithm. Each residual graph in the example only contains the residual edges with a capacity larger than 0. Each residual graph may contain multiple iterations of the perform operation loop. The example can be run here interactively. Practical implementations. while the generic push relabel algorithm has O time complexity. Efficient implementations achieve O or lower time complexity by enforcing appropriate rules in selecting applicable push and relabel operations. The empirical performance can be further improved by heuristics. Current edge data structure and discharge operation. The current edge data structure is a mechanism for visiting the in and out neighbors of a vertex in the flow network in a static circular order. If a singly linked list of neighbors is created for a vertex, the data structure can be as simple as a pointer into the list that steps through the list and rewinds to the head when it runs off the end. Based on the current edge data structure, the discharge operation can be defined. A discharge operation applies on an active node and repeatedly pushes flow from the node until it becomes inactive. Relabeling it is necessary to create admissible edges in the process. Discharge. While U greater than 0 if current edge U has run off the end of neighbors U, relabel rewind current edge U, else let equals current edge U if is admissible. Push else let current edge U point to the next neighbor of U. Active vertex selection rules. Definition of the discharge operation reduces the push relabel algorithm to repeatedly selecting an active node to discharge. Depending on the selection rule, the algorithm exhibits different time complexities. For the sake of brevity, we ignore S and T when referring to the vertices in the following discussion. FIFO selection rule. The FIFO push relabel algorithm organizes the active vertices into a queue. The initial active nodes can be inserted in arbitrary order. The algorithm always removes the vertex at the front of the queue for discharging. Whenever an inactive vertex becomes active, it is appended to the back of the queue. The algorithm has O time complexity. Relabel to front selection rule. The relabel to front push relabel algorithm organizes all vertices into a linked list and maintains the invariant that the list is topologically sorted with respect to the admissible network. The algorithm scans the list from front to back and performs a discharge operation on the current vertex if it is active. If the node is relabeled, it is moved to the front of the list, and the scan is restarted from the front. The algorithm also has O time complexity. Highest label selection rule. The highest label push relabel algorithm organizes all vertices into buckets indexed by their heights. The algorithm always selects an active vertex with the largest height to discharge. The algorithm has O time complexity. If the lowest label selection rule is used instead, the time complexity becomes O. Implementation techniques. Although in the description of the generic push relabel algorithm above, H is set to 0 for each vertex U other than S and T at the beginning, it is preferable to perform a backward breadth first search from T to compute the exact heights. The algorithm is typically separated into two phases. Phase 1 computes a maximum preflow by discharging only active vertices whose heights are below n. Phase 2 converts the maximum preflow into a maximum flow by returning excess flow that cannot reach T to S. It can be shown that Phase 2 has O time complexity regardless of the order of push and relabel operations and is therefore dominated by Phase 1. Alternatively, it can be implemented using flow decomposition. Heuristics are crucial to improving the empirical performance of the algorithm. Two commonly used heuristics are the gap heuristic and the global relabeling heuristic. The gap heuristic detects gaps in the height function. If there is a height 0 less than h less than v, for which there is no vertex u such that h equals h, then any vertex u with h less than v has been disconnected from T and can be relabeled to immediately. The global relabeling heuristic periodically performs backward breadth first search from T and GF to compute the exact heights of the vertices. Both heuristics skip unhelpful relabel operations, which are a bottleneck of the algorithm and contribute to the ineffectiveness of dynamic trees.